It's on air.
On air. All right. Welcome on air. Welcome here. I'm also sitting right now. Normally I'm standing, and I'm just doing that so that hopefully that everybody out there on the internet can hear me better than if I'm wandering around. So thank you all for coming. I'm, I guess, a big advocate for what we do here, partially because I was born in a country that sort of pioneered this standard. And I was inspired early on in my career. I started out as a woodworker, and in that profession, I already learned about natural materials and really how you can leverage those for high performance construction. And during my studies, I was able to take sustainability classes, which are offered here just the same, and also classes in green construction, I suppose you would call it. And most of those classes were really more about the failures of early attempts to make high performance buildings. And those failures are often the best teachings, and you can learn a lot from what worked and what didn't. And when I went through school, Passive House was in its infancy, and it was sort of looming out there, but it wasn't mainstream yet. And that really changed in Germany over the course of about 10 years between 1990 and 2000. And by the time I got here, I found a marketplace that was really consumed with a bigger building, not necessarily a better building. And there were booming years going on. And I had to find my way into living here and working here. But within about 5 years or so, I came back to my origins, and I found other people here in the United States who were interested in Passive House, and people who were starting to offer training and certification for building and for people. So I participated in that essentially from the first day, and therefore sort of became a part of that community that's here today with all the helpers and the members of the Alliance. So that's sort of my background. Also, TE Studio was really founded on the premise of bringing Passive House and high performance buildings to the marketplace. And we go well beyond just Passive House because that standard focuses so much on energy efficiency. And I think we can all agree that a good building should deliver on more levels than that. And so I have a few bullets up here on the screen that showcase some of the other things that we try to bring into projects. Just recently, within the last couple of years, I also joined the INTEP group, which is an international company that offers commercial real estate consulting and design. And the leader of that organization here was Stefan Tanner, who built the first certified Passive House in North America. There's a picture of it on the wall over there. It's called the Bio House, and it's in Bemidji. So most people wouldn't know that, but the first Passive House in North America is actually in Minnesota. And it's in climate zone 7, where it's really, really cold. So it does work up here. All right, but today we're going to talk about a different project. We're going to talk about the MinnePHit House. We're going to talk about retrofitting. And I titled this Holistic Energy Reduction Retrofit because we try to, again, hit on more points than maybe just energy. And with Passive House tools. Obviously, we use the standard, we leverage the standard to quantify what we're actually doing. The house is set in climate zone 6. That's where we live up here in Minneapolis, Minnesota. It's got sort of a funny name that the homeowners came up with, actually. Minneapolis and EnerPHit. EnerPHit is the Passive House's brand name for retrofitting to Passive House standard, and they simply combined it and coined MinnePHit. So that's what it is. But it's the Brazelton family that commissioned that house, and they're the ones who live in it now. Just a couple of things to clarify here from the beginning. This is way more than weatherization, the work that we do. And it's sometimes confused with weatherization and sometimes tossed into the same bin. And I crossed out the caulk here, and not that we wouldn't use it, but in the weatherization programs, the homeowners, when they come and they get a little bit of education, they usually get sent home with a tube of caulk and an energy-saving bulb. And what I'm trying to suggest is that that's not enough. And to illustrate that, I'm kind of a car nut. I often use cars because people understand that. And so what we deal with when we start is the building equivalent of that. I think it's a fair picture for what the housing market offers here in the Twin Cities. We have one of the oldest housing stocks in the nation. I think it's 65 or 66 years on average for the urban core. This may be just a little bit older, but it works, I think, as a comparison. And when clients come to us, they often don't realize that this is really what they own, but they do have a vision of what they want, and it may look like this. Okay, so that's interesting. I'll just make that leap one more time. And the good news here is that that can actually be done. Partially because of the way that buildings are constructed here. Wood construction is great for, it can be modified very easily and by just about anybody. So we can do a lot with wood construction. The other good news is that other people have tried, and there's many concepts out there that you can ladder up to and leverage, and passive house being one of them. So this is not out of the question. It's just a matter of whether you choose to do that, and you can actually afford to do that. The program that we're leveraging here again is called EnerPHit. They have a little logo here. This, I guess, is the German logo. They just went from draft to final standard. When we started this project, it was just a draft. And so all the criteria weren't quite clear yet. Here's sort of an excerpt of the front page of the manual, I suppose, that they have and that they share. And what it is essentially an energy goal that is set for space conditioning, heating, and or cooling. Also an energy goal for all the energy that goes into the building accounted for at the source. So we go all the way back to the provider. We want to know what the house consumes, but we also want to know how much does the provider have to make to supply the building, because that's usually where the environmental damage is being done. And that's also where loss factors come into the equation. Some of you may or may not know that if you use a kilowatt hour of electricity in your home, your power plant has to make about 3 kilowatt hours. And most of that is wasted as either heat or in transmission losses. And so it's a significant loss factor, and that needs to be taken into account. And these two goals, the space heating or space conditioning limit and the source energy limit, are similar to what you would find in new construction passive house, but they're just a little bit more lenient as the Institute recognizes that a passive house retrofit deals with existing conditions, and you can't make it perfect. So it allows you a little bit of wiggle room. There's a third limit here in the mix, and that is an air tightness limit. Some of you may have seen a blower door before or heard about air tightness testing. It's also on the docket for a new energy code here in Minnesota. I think the debate that's happening right now is about 3.0 air changes an hour at 50 Pascal. We have a limit for new construction in passive house of 0.6, and for retrofits it's 1.0, so it's a little bit more lenient again as well, but it's a fair margin from what what is being discussed as being implemented here in Minnesota. Those are really the big three. I won't bore you with all the details. Maybe big picture, there's a couple of ways to do a passive house retrofit. You can certify an entire building based on its performance, or you can certify it based on individual components, meaning rather than meeting an overall energy target, you show that you retrofit the walls, the roof, the slab, and the windows to a certain level of performance. So there are two tracks that you can select essentially. Because in some instances, you may do everything you can to the envelope and still not get to the overall goal, and that's still okay, that's still acceptable. The two that are listed here, EnerPHit and EnerPHit I, the difference here is really just where is the insulation that you're adding. EnerPHit plus I is for buildings where most of the insulation is added on the inside. And that is not preferable. That's a last resort, really, because it produces building physics challenges. But it can be done, and so they have another track for that, just to recognize that as well. Again, I won't give you all the details. These are sort of the big highlights about doing EnerPHit. I'll give you a little bit of background on this particular project. As you can see in this slide, 1935, that's the year the home was built. These are completely different times. And I think that image illustrates that, well, this was given to me by the homeowner, and I think he said this was taken in his neighborhood. And you'll see the people shoveling coal, and homes that from that era usually have a chute for coal, and that's how they were heated. And so between the building envelope and the mechanical system, this was a completely different time and a completely different animal. You remember the vehicle, and I posted it here again. These are actually photos of when we started This is the front facade, the street facade. It's a 1935 fake Tudor. We don't know exactly if that had ever been altered in terms of its shape. We know it had been retrofit at one point, but it may have been built exactly like that or added onto, who knows. But that's how we found it. This is the south facade. This is the east facade, the back side of the house and where the backyard is. And then we have the north facade right there. I'll give you a couple of interiors and some detail here. The house had 2 stories above ground and a basement, 1,200 finished square feet, and that's counting all 3 levels, 2 bedrooms, 1 bath, and there are 5 people living in it. It's a family of 5. So it's tight quarters. In this next image, you can see all the kids were sharing a bedroom. You can see in the second slide to the right up above the railing, which it doesn't just appear low, it was low. There were many code issues in this building, this being one of them. Standing next to that gave me a kind of a buzz. It was about knee high or so. Bathroom, the only bathroom in the house on the 2nd floor, which that is a minor inconvenience, I suppose. And also with outside walls. And so that bathroom was not only small and in a bad location, but it was also very, very cold in the winter. And then the fireplace that I'm showing here is sort of indicative, again, of its age. That would have been maybe used to heat the house at some point. We don't know. At this point, however, it was terribly drafty, going the wrong way, backdrafting. So the whole house reeked of soot. And that was really prevalent depending on changing weather conditions. It would backdraft through that quite a bit. And we blame some of that on the airport noise reduction retrofit the building got in the, I want to say late 80s, maybe 90s, not so sure. That retrofit really produced some bigger problems for this building. I should say that a retrofit like this was obviously targeting an improvement, so that it would be quieter in the building. What they did when they retrofitted is they added storm windows to the outside, single pane. So the window system was single pane, double hung with single pane storm window. So not necessarily a high performance assembly. And when they put that in, they didn't really worry about air tightness. These IR pictures here really showcase that well. The darker the color, the lower the temperature, and you can see the bypasses and the lack of performance in the glazing. The building got a mechanical retrofit in that, the left-hand side is just a plumbing protrusion that is a terrible bypass, but on the right-hand side, you can see the grill of an air conditioner that was put in the attic. And so they had the machine outside of the insulated building envelope, but the grate going right through the ceiling into the rooms below. And as you can see, this is sometime in December, I want to say, there's air dropping out of that grate at 39-degree temperature, and this is while the house is being heated. The other thing that we found when we went in early is that the interior surface of exterior walls was actually at the freezing point while the house was being heated. So we had about 36-degree wall temperature in a house that's being heated. The mechanical plant had a hard time getting above 64 degrees in that building. That was hard. I don't know that it would have ever gotten up to 70 in there. We tried, and at 64 is about as warm as we saw it. The basement air temperature was maybe 50 degrees. And this is all conditioned interior space for people. We did manage to get a blower door test from this building, and that's where it came in at 8.5 air changes an hour at 50 Pascal, 2100 CFM. For those of you in the trade, that probably means something. It's not as terrible as some buildings we've tested, and that's probably due to the fact that it had the noise pollution retrofit, but it's pretty leaky. I bet if you went back and you figured, what do all the holes in the envelope amount to in that building, it would be multiple square feet. So under standard conditions, the building was leaking so much air as if a couple of windows had been open year-round. That's what this sort of represents. And when we go in, not just doctors, but architects too, we deal with pre-existing conditions. We try to scrutinize buildings fairly closely. And so we did the same thing here. And you can see a few of them, some of the highlights. You may notice the dryer vent in this image essentially blowing onto a retaining wall. This is by itself is not terrible. It's just not right. You can also see the stucco cracking all around the windows there, and that's indicative, of course, of a weather barrier failing. On the inside, oops, skip the slide here. No, I'm sorry. The right-hand side there, you can see the plastic that people put on the windows, and that's pretty common around here. And there's nothing wrong with that. But the problem with the window wasn't so much that it was leaking through the window, but it was leaking around the window. So the fact that there was plastic on the window didn't really help because most of the air was leaking around the window and through the window trim. And so this really produced a minor improvement. Here's another image of the second floor balcony, and I think structurally that speaks for itself. Here's an image of the home office, and because of the comfort challenges in the building, the homeowner simply decided to fill the window openings with foam panels. And after a while in the house, they never bothered to take that out. So they were in there year-round. They traded daylight for comfort. Here's the mechanical system, and I have to say this was taken on by the homeowner himself. He put in this new system with an on-demand boiler, and there were some code challenges between this thing heating the home and making hot water, where this wasn't actually a code legal system. I don't know if that had anything to do with the lack of performance, but at the end of the day, it was clear that we would recycle that or change it anyway. So it wasn't one of our concerns, but mechanical systems we find in these buildings, they vary greatly. This was certainly a newer setup, but that didn't mean that it worked very well. And in some cases, we find very, very old equipment that doesn't work at all. Here's just a couple more slides illustrating, again, these vast temperature differences in bypasses in joist cavities. You can see disturbed insulation on the right-hand side there. On the left, I think that's just a corner of a room with probably some sort of duct or vent going to the outside, so you can see a joist cavity cooling off, again, allowing temperatures to drop into the 40s inside conditioned space. So at the end of all that, we got to take a tally of where we are. And what we did here is we have sort of a checklist. We like lists. We're German, so that always works for us. We have structure, yes, and the structure held up for all these years. Weather barrier, maybe. Stucco was on there. We had windows that would open and close, but how good they were, who knows. Insulation, no. We did find a little bit, I think, in one corner of the house, which was sort of odd. One room was insulated, the rest was not. And then any other insulation in the basement, for instance, was put there by the homeowner just recently. So no insulation. Air tightness, I think at 8.5, it's fair to say there wasn't any air tightness. Moisture management, well, interestingly enough, in these older structures, that sort of works, right? Because they're leaky, they're drafty, we got wood construction, and so it sits wet, and then it warms up outside eventually, and it can dry out, and if there's no insulation in the cavity, that moisture isn't really being absorbed and stored. So the building held up, no doubt. 35 to 2010, whatever that is now, so many years it held up. And it didn't fall down, so that worked. And it's beyond its design life, because we assume wood construction is a 30-year life cycle. Ventilation and air quality, not. We had the backdrafting issue I talked about. There were no means of exchanging air in the building, no mechanical system to do that. So that was poor. Comfort, I gave that a 2 no's, because that was really terrible. I had enough of it after a day of measuring. Daylight, very little, and that is due to the design of the building, really. You saw most of the windows are kind of small, and that's really how they were designed back in the day. So that it's not really a flaw, it's just a fact. No great daylighting. Durability, we assume wood construction is a 30-year product unless you do something special with it. We all recognize these buildings continue to live on way longer than that, but that's because we maintain them and heavily retrofit them every so often. Design was a sign of the times. You can think of that what you want. It is what it is. It fit the neighborhood, and that's okay. And so then the next question was, now that we know all that, where do we go? What do we do with that information? Here's another list. I think there's 2 more in the slideshow, so bear with me. We call this the laundry list because it could be endless. And we developed this with the homeowners, I should say, too. It's not just us doing our work here, but in this case, the Brazeltons were, of course, heavily involved. What we needed to find in that building were 3 more bedrooms, 2 more bathrooms, a mudroom, a better kitchen, better living areas, a homeschool room, safe stairs, a weather-tight envelope, a durable structure, healthy interiors, comfort in daylight, low operating cost, and energy performance. Okay, that was the list that the homeowners brought to us, and we essentially brought back the EnerFit as a tool to, counteract some of the shortcomings here and guarantee a certain level of performance. But everything else you see on that list is really standard architectural practice, trying to find the rooms and improve on some of the conditions. So it's a mixture of both. This is the image that we came up with early on. It was a rendering of the future version, and you can see the little car up in the corner. This is now indicative of the high performance piece. We try to stay within the design that's prevalent in the neighborhood. We also worked with the homeowners here, of course, to reflect their tastes, and so that's what we came up with. So then naturally, the next question is, how do we do that? How do we actually get there? And I'll give you another car. Some of you may have seen that in other slideshows. This is actually one of my favorite ones, simply because, that spoiler didn't make that a sports car. And, when you deal, again, with a tube of caulk and the energy-saving light bulb, that doesn't necessarily equal an energy reduction retrofit either. And that's just what I'm trying to say here. So we try to, deliver something beyond that. And we call that the holistic approach. And the way we do that is we try to set some firm goals for the performance and for the design, things that we hold ourselves accountable to. We try to do an overlay of architectural programs here. What do we have and what do we want to have? And in this case, we needed to make the home safe for people. That was a big piece. We need to control temperature, air, and moisture in the building and add ventilation for the air quality. We need to make the envelope air and weather tight. And air tightness, I'll just stop here for a second too, because we got a lot of questions on that. Why would you ever make a building airtight? Isn't that bad for it? Isn't it going to rot? And the short answer is no, it isn't. If you make it really airtight, you actually did something to prevent it from molding and rotting, because what molds or rots a building is warm, moist air from the inside escaping the building envelope into assemblies, a wall, for instance, where it can hit or meet cold temperatures. And then it can fall out as condensate. In the winter, it may freeze, and that cycle may continue, and you get more and more and more ice. And once the thaw comes, then it ends up as liquid water in assemblies. And then depending on the drying potential of the wall, it may or may not dry. And over the cycle of multiple years, that sort of process may accumulate problems. And that's where structures can fail. So airtightness is actually meant to counteract that sort of process altogether. And on the other hand of or the other side of the coin here, it helps with energy performance, because you're not leaking that precious warmth or cold air from the inside to the outside. You're not trying to heat the whole world. You try to just contain it to the building itself. Add continuous insulation. Early on in the introduction, when I talked about the exterior and interior insulation. Continuous insulation is best put on the exterior, and that's what you'll see in this project, although there were some areas in which that wasn't doable. Assess moisture transfer through the shell. This is something that I cannot stress enough how important that is, especially to the colleagues, anybody who dabbles in high performance buildings. Whenever you change a system from what we all know and understand, it's important to assess moisture transfer, because it'll change, it'll alter. Drying potentials are being altered when you use high levels of insulation. So that becomes an important part of the design puzzle to understand that. And then last but not least, implement robust climate zone appropriate assemblies. So we want to choose materials and systems that we feel will survive the onslaught of what this climate zone here has to offer. And it's one of the more exciting places to build in the world. So, all right, energy targets, just a simple one here. Reduce loads and air leakage. That's pretty straightforward. We're aiming to reduce the heating load by about 80%. You saw in that little film earlier, if you build a new passive house, it's about a 90% reduction. Again, in a retrofit, they give you a little bit more leeway, so it'll be about 80%. Overall energy consumption in the building cut by about 2/3. We can't do that without the help of the homeowner. That's important, because their usage pattern in the building will affect that. But that's usually what a passive house brings. And air tightness in this case, because we knew what it was before and what it needs to be, we needed a 10-fold increase in that. And that's how we did it right there. And we're done. So, you know, for those of you who live in Minnesota, you wouldn't go outside in the winter with just a t-shirt, right? So you put a heavy coat on. And to everybody, that makes perfect sense. If you go out in the winter, you want to stay warm, you need that heavy coat. And that's really the concept that any sort of passive solar design and especially passive house has pioneered over the last 20, 30 years is in those colder climates, put a heavy coat on the building. So it's kind of like the egg cozy here. We try to maintain that precious energy that's inside the building throughout all seasons. And that's really the only trick. It's how do I contain it? It's a thermos bottle if you want. How do I ride through the season, ride it out, kind of like coasting in a car? I'll give you a quick sort of architectural overview of where we went with the building. I think this is important to understand all the different, you know, sides and facets of this. This is what's called a demo plan, but it shows the existing condition of the basement. It was a square 22 by 23 feet, so it's a tiny footprint, if you wish, and it had a slab on grade construction to the north, so there was no basement under that part of the building. And I'll overlay here now how we retrofit it. You can see the main body of the house was retrofit. The north side of the house ended up being what we called reconstruction, and you'll see that in later slides. It was so badly damaged over the years that it had to be rebuilt. And then on the east side, we ended up building an addition because we did need to find a few more square feet. So technically speaking here, we have sort of three parts to this project. I'll show you what that looks like here on the, I'm sorry, where are we? On the first floor plan. You'll see the existing condition again. You'll see the overlay with the new, and now I'm highlighting the retrofit area again, the reconstruction and the new construction area. And what you're looking at is essentially a reshuffling of spaces. I'm not sure that we need to go into every one of them, but in the retrofit area, we reshuffled kitchen, dining, and living. In the reconstruction area, we created a powder bath on the first floor, a good entry, and a mudroom. And that used to be a kid's room where it says up there in the corner. It's now a mudroom. And on the addition side, we created an open kitchen and a dining living area. Here's the final product. This is probably the better slide. So you can see it's an open floor plan, which is what most clients want these days. That has nothing to do with passive house or passive house retrofitting. This is the architectural component here. The addition had a footprint of a total of 800 square feet on 2 levels, so 400 feet we added on the first floor and the second floor. Second floor plan, you can see there's the 2 bedrooms, the stair in the middle, the single bath, and then the office that I showed you. And the office was sort of almost a half a flight of stairs down. The stair was really bad, didn't meet code, and the second floor wasn't all on one level, which presented its own challenges in retrofitting. Here's the overlay. Again, retrofit portion, reconstruction portion, and the addition portion. And then I'll jump to the finished product, and you can see we went from 2 bedrooms to now 4 bedrooms on the second floor. We added a master bathroom in the master suite, your lower right-hand corner, and a little entry area that is a sort of a walk-through closet, if you wish. And we expanded on the existing bath and separated out a toilet room. And the hope here was to just give the home better flow. With 3 kids, they can now separate out between toilet and usage of the bathroom. They have 2 vanities in there. They're all girls. That'll be interesting in a few years, but we'll see how it goes. So this is the floor plan and footprint that we ended up with. This is our concept sketch that we use when we talk to clients and when we give presentations like the one today. Basically, what we're looking at here is a generic section of a building. This could be any home, really. The part on the right is an illustration of what we normally find. And it's pretty similar to what we found here. You find below-grade assemblies with no insulation whatsoever, skinny above-grade assemblies with some insulation, and usually there's a little bit in the attic or in the roof up top. But that's pretty common. And then there's a large mechanical system that's trying to make up the difference, because a mechanical system is really an equalizer, right? You're trying to maintain a certain condition, and if you can't maintain it all on its own, then you have to generate that, and that's what that system does. Now, the change over here to the left-hand side now illustrates we're adding to the existing assemblies. We're adding more insulation, all the yellow stuff. You may also notice there's sort of a fine red line in that assembly, and that means we're adding air tightness. There is a distinct layer that we identify somewhere in that system that does nothing but maintain air tightness in the building. And we figure out where that is, and we show it on all the drawings, and we educate everybody on the job site that that's the part of the building that you need to be careful with in execution and not damage. We bank on a little bit of solar heat gain. Passive house at the core is a solar model. Now in a retrofit, we can't site the building anymore. It's already there. We also can't pick the neighbors. And so it is what it is. But even in a retrofit condition, you can bank on some solar heat gains. So we have that in the mix. We have assemblies that are conducive to it. So the windows we use are high performance products that insulate well, but allow that solar heat gain to come in. And that's the same we used here. You can also see the ventilation system as being sort of the main component now of the mechanical setup. So we're mostly concerned with ventilation. And then we have a small backup heating system usually in these buildings, and we need a source for domestic hot water. Any sort of renewables are completely optional. And we said that at the top here, passive house doesn't require those. So whether you want to become an energy plant or provider is completely up to you. It's not required to meet the standard. And the renewables are also not used or leveraged to generate the performance of the building. It comes all out of the system of the building itself. There's a couple of opportunities that we have. If we're retrofitting below grade, for instance, we can add waterproofing. We can deal with radon if there are issues like that. Again, this goes beyond what maybe passive house would govern. That's part of the holistic approach. You want to tie these things together when you have the chance to do so. These are some of the assemblies that we used. I know these are technical drawings. They don't work for everybody, but you're looking at a horizontal section on your left and a vertical section from basement to the top on the right. The colorless or assemblies that don't have a background color are the ones that were there. So if you look at the right-hand side, you can see the big concrete basement wall on the bottom there and a footing, and those things were obviously there. And there's a floor system above that was there, and there is a 2x4 wall system above that was there. So everything that has color are things that were added. In this particular case, we had the added challenge that the roof was structurally not sound, and it also started right on top of the windows. And that presented its own challenges structurally. And pretty early on, we found that that wasn't sustainable. We had to do a new roof. And we used the opportunity to build the walls up to a regular ceiling height on the second floor, which previously it didn't have. So you can see a little bit of a knee wall basically extruding above the existing wall. It's a truss roof system up there, so that's pretty standard construction. You can just see the higher levels of insulation. I'll give you a few figures just to put things in perspective. Had we built this to Minnesota building code, in the grade or in the ground, the Minnesota code would have required an R value of 10. To make the energy goals here, we're above R30, so about 3 times the insulation value. Above grade, again, code requires about an R19. And the caveat there is it's really only looking at the place in the wall where it's all insulation, because there are parts of the wall that are wood. If you average an R19 wall, it may be only an R13 for the performance of the entire assembly. But that code doesn't even look at that. It says R19. The walls here are about R45. So we're looking at a factor 2 to 3, 2.5, thereabouts. And when it comes to the roof, Minnesota code requires an R value of 38. We're at 77, so we're about twice that. And going back to the movie that I know the webinar people didn't see that probably, but those assemblies do end up being almost on the wall side, 1.5 feet, and the insulation level in the roof is 22 inches. So that's pretty similar to what the movie talked about you would find in Sweden. And that's not a surprise to me because we have similar winter conditions. On the left-hand side, you see a horizontal section. And this is just to illustrate how our new wall works on top of the old wall. This building was furred out, meaning we added additional framing to the outside of it. And then all cavities were filled with insulation. And I'll give you plenty of pictures here in a little bit to illustrate that. I think for most of you, it's probably easier to see that in a picture than a drawing. So these are assemblies. The next part of the equation for us is in the details. And the devil is really in the details when you make a passive house. And so we look at protrusions very carefully. We look at connection points very carefully. And we look at these insertion points of, for instance, windows. And that's what I'm giving you here. We created a page that deals exclusively with windows. And it shows in section, horizontal, vertical, and even in an elevation, what the new window looks like inserted into the retrofit wall. And this is really what we spend a lot of our time and our expertise on, is figuring out these detail junctions. And when you're getting into a retrofit like that, and Ryan, who was the builder for this project, is in the room, and he'll join us later for Q&A. This is where the rubber meets the road, in the design and execution of these details. When you want to get to these air tightness levels we talked about, and moisture management and durability, it's critical that these assemblies are designed properly and executed properly. And it takes a very diligent builder to see that through all the way to a successful blower door test, which is one of the main testing methods at the end of construction to see if it all worked. Here's a slide of the mechanical system after the retrofit. We often do these little napkin sketches. It doesn't have to be fancier than that, really, for most buildings. When you build a passive house from scratch, you wouldn't necessarily use a gas boiler. In most cases, that would be overkill. Now, we're dealing with a project here where that infrastructure was existing. So it made sense to leverage that. And the homeowner had made an investment in a boiler that could ramp up and ramp down in its capacity, so it could supply low loads. So we had infrastructure that we could tie into and expand upon. So on your left, what you're looking at is just a diagram of a on-demand boiler that is essentially heating the house through in-floor heating pipes and a tankless domestic hot water heater for on-demand hot water. So that's really our heating plant. And on the right-hand side, you can see the ventilation machine in a schematic and a pipe that we use for ventilation. And we have some of these products here, so we can break them out later and you can touch them and see them. So that in itself really constitutes the extent of the retrofit. The building was designed, I should say, with a mini split air conditioner in mind. The clients haven't put that in yet, but for the design, it is vital to have it, partially because they didn't shade the windows the way that they maybe should be shaded, so they'll take on a little bit more heat gain. But also, one of the things that we learned, and this is a good sort of message, I think, for anybody working on passive house projects, if you're dealing with an airtight, highly insulated envelope, you can heat it very effectively with your activities inside. And just like in the movie earlier where the woman said, you know, I can walk up and down the stairs and create heat in the home, it's true. And so if you had a party and you invited a bunch of your best friends and you did some heavy cooking, you will increase the interior temperature in a passive house. And in this particular building, we were there last week. Ryan was there with us. We did a blower door test. There were about 5 of us in the building. It was all sealed off. It was a warm day. We started at 76 degrees, but inside, by the time we left, it was 78 degrees. So just 5-6 people working inside the building were able to heat it. So an active cooling source helps you deal with those internal gains when you have those moments where that becomes excessive, but they also help you with heat gain you may take on from the sun. That may seem wasteful, but it really isn't, because in the larger scheme of things, those loads are tiny compared to what we have in heating loads. And again, we're averaging heating and cooling loads. Both of those have to meet the same standard over the course of the year, and that is not a challenge, at least in our climate zone. The other way to cool down a house, of course, is to open up your windows or to let your ventilation system go into overdrive on those days where it is cooler outside than inside. So those common sense still works. We haven't overwritten that. This is a schematic we got from the vendor. We often partner with vendors, and in this case, Zender did the mechanical ventilation system for the building. And it just illustrates the lines that go from the machine to individual rooms and back to the outside. And again, I'll show you what that looks like in slides as we go through here. All right, so let's have some fun with it. That's great. Who said oh? Um, so when you dig into an older building, it's the proverbial can of worms, obviously, and so was this one. This was no different. So what we found was the chimney that gave the home a lot of character was actually highly unstable. Part of it had already collapsed inside, and that was maybe also a part of why it backdrafted, because there were bypasses. I don't know. So it ended up coming off the building. The north addition, or we don't know if it was an addition, but the north part of the house that's in the process of falling in this picture, um, had suffered badly from water damage and was irreparable. And so we had to respond, on the fly and come up with a new design for that part of the building. Here's another image from the backside. And before we get too far into this, I have to say that a lot of credit on this really goes to not just Ryan, who's with us here, who's a contractor, but especially the homeowners. Desiree and Paul Brazelton, they did a lot of this work themselves. And I know they had help from family and sometimes neighbors, and I don't know, maybe even random passersby. I think this job was much more monumental than they had ever imagined. And just picking the stucco off the house, I think they had this fantasy of you hit it with a hammer and it falls off. And I think it came off in dime-sized pieces in reality. So that was a very different equation. Here's a nice detail shot of what that looks like under the stucco. So most of the wall has actually disappeared, and you're now in a place where the stucco is holding up the home. Looking at you because I know you have a stucco house. So stucco can be perceiving where a house looks really great from the outside, but that's really what's happening on the inside. Not on all of them, but it can. Here's another close-up of the chimney. And at the end of the day, what we ended up doing is we basically layered our air tightness layer all the way across the chimney. And the chimney that you saw in the rendering before and that you'll see in the final product is completely fake. And its only purpose in life is to give that home street appeal. That's it. So I keep that in mind. That home no longer has a functioning fireplace. I'll show you a couple of shots here of the basement and how the retrofit in the basement worked. I don't have any of the real good action pictures, so I should ask for those. But in this picture, the slab down below is already gone. So you never quite know with these older homes if they have footings, what's happening at the slab. And we identified that by busting a couple of holes. And one of the things that we identified with the homeowner is we really need that square footage down there. They needed that space desperately. So early on, we made the decision, this is now inside of the conditioned building envelope. And what that means is it needs the same insulation levels really as everything else. And so the first order of events here was to eliminate the basement slab. Now, a lot of these older slabs are not very thick, and I'm not sure how bad this one was to get out. But that's usually something that can get done quickly, especially if you have access to the outside conveyor belt or something to get rid of the garbage. I don't know that was possible here. I remember people bringing buckets up and down a ladder, which I'm sure was great fun. Yeah. We found another opportunity here. We actually gained the homeowner, or found the homeowners a few square feet. You can see that framing in the middle here, and that's the center load-bearing wall. That used to be a concrete wall. Now, there were two problems with that. It was sitting on the slab, which needed to go, and it sucked up a lot of space. And so that would have presented a significant thermal bridge had we left it in place. So we made the decision to eliminate the center load-bearing line, which for most builders and homeowners, that's an exciting thing if you take away the part that's holding up the house while it's standing there. And there are ways to do that, and you can quiz Ryan how he did that. But eventually, we ended up replacing that center load-bearing line with a wooden wall, which is much skinnier, and we were able to sit it down on a fully insulated footing. So what you're looking at the bottom of that is a new concrete footing that is completely encased in foam. And then in the next stage here, you can see how on either side of it, now the ground is being excavated and replaced with foam. The white stuff on the upper side here is EPS foam. So we're basically replacing dirt with insulation. Here's another slide, sort of a progress now. Now the entire surface is filled in, and side to side, wall to wall. Then we have air tightness that we need to maintain. So we introduce a polymembrane in this particular case. And we were also going to heat the slab just like all the other floors in the house. So you can see the heating pipes. And at the foundation, and at the perimeter, we had to get really fancy with smaller pieces of insulation to essentially encase the footing itself and disconnect it thermally from the new slab. And that's what that looks like. And at some point, you end up with skinnier pieces of insulation. But again, it's a retrofit. We're not building this from scratch, so we have to make do with the room we have. All walls were insulated on the interior. So that insulation that I think Ryan's foot is on right now there is essentially connecting to the wall insulation later. So we do have now continuous insulation from below the slab all the way up the side walls. This is what it looked like once the secondary stud wall was placed and the walls were foamed. We try to not use too much spray foam because it's a crude oil-based product and it creates a composite where in a paradigm where you think about this home coming down at some point, it's going to be tough to recycle these bits. But it is a lifesaver in some conditions like this one where you're simply out of options. If you want to do it in a tight space, and you still need a place to hang your sheetrock, this combination here was very effective to get us high R value in only about 5 inches. This is something exciting. You don't see this very often. This is vacuum insulated panel insulation. It's a product that came out of industrial processes, and it delivers an R value of 30 for 1 inch of thickness, which is about 5 times more than the best spray foam insulation out there today. This is a product that we use when we're absolutely out of other ideas. Like this one, we had an existing stairwell with a stair being barely wide enough to meet code. So furring in our walls, adding more insulation was not an option. We needed to get the R value in virtually no space at all. And so we used this material in a small area application here and provided a continuous about 30 R value even across this area where we had no space. That we sometimes use it behind shading devices or in areas where walls are diminished in depth for whatever reason. It's readily available in the marketplace, and we're grateful for that. So we have some high tech here, but that's about as high tech as it gets. This is an above grade assembly, and I love this slide because it sort of shows 3 stages of improvements, if you wish. There's sort of old, fixing of old, and then new. In our wall assembly above grade, what we did is we layered OSB on top of the exterior sheathing, on top of the old wall. And we used that OSB to air tighten the building and to vapor manage it. As it turns out, OSB has a perm rating that can be used to create a vapor retarder. And it also makes great air tightness. And so we used that product, we layered it onto the exterior sheathing of the building and taped that up and achieved air tightness and vapor management in one fell swoop. And there'll be a couple more slides to show that. Here's a sort of interior framing condition showing some of the new framing of the addition in the ceiling and an old ceiling still hanging on the inside of the building. And what I'd like to illustrate with these slides really is the redundancy, but also the flexibility of wood structures. And I said that earlier. You can do almost anything with a wood structure because you can just hack into it and you can sister on, you can hang from and ledger off and cantilever. And a lot of that was done here as well to create the new floor plan layout and create the assemblies that we wanted to create. So that's really what you're looking at when you see these slides. When it comes to new construction, and this is a photo of the addition, you can see this looks just like any other home. There's 2x4, in this case, walls. Some cases they would be 2x6. OSB sheathing on the outside. So this is really built like any home would be built in this neck of the woods, at least for part of it. And this is our interior stud wall. This is the load-bearing wall of the home. And up to this point, we haven't really changed any paradigms whatsoever. These are the roof trusses set on top of those walls. And again, this would look exactly the same on any new construction building that you would find here and probably anywhere in the country. I told you earlier that we added to the existing walls to generate some height. So that little knee wall you see on the left-hand side is what that looks like. And again, it's standard framing. And I just like these pictures again because you can see some of the old and some of the new coming together. It's like a puzzle. Here you can see the original sheathing of the building was lapboard. And at the corners where it rotted out, the builders decided to rebuild some of the corners just to give it strength. And you can see from the rear of the building, working their way forward here, they're setting the OSB for air tightness and vapor management, and they're setting the trusses on top of the roof. And this is just sort of a progression here of that all coming together. Now we're looking at the front facade of the building. And this is a stage where the envelope, at least the airtight envelope, is almost complete at this point, and the roof is completely set. So at this point, it's almost a traditional building with a traditional truss system on top of it. In normal construction, people would side over this, insulate the cavities, and walk away. So to this point, we've essentially made something anybody can make. Yeah, quick question here.
Can you go back 4 slides to the first, the trusses, and emphasize the raised heel truss?
Yes. So the question, I'll repeat that for the webinar, was, can I emphasize the raised heel truss? And that is essentially, I'll point to that here in the office because I can. This bit right there. And it offers a certain height, and that height is needed for the amount of insulation that's going in the roof later. So in standard construction, the top member and the bottom member may have timed out at that point, and here there's an actual height there just to get enough insulation in there. Thank you for that. This is another picture to illustrate that, but the other piece it illustrates is we essentially hung the back end of the roof trusses over the structure itself into the plane of the new fir framing. So once we puff out the walls with more framing, everything times out and can be sheathed up and closed in. So in the design, we already accounted for the new thickness of the walls. You can see the roof sheathing going on here. Here's another corner picture of the OSB coming together. Again, another picture showing old and new, and you can see there's basically all stages of construction happening at the same time. There's still old on the left and probably some demo to do. There's some old insulation left, and there's new construction on the right. And that would be pretty typical for this kind of thing. You're weaving it in. This is how we covered over the chimney. I said that earlier. Our air tightness layer was eventually 100% completed over that chimney so that it no longer presents a liability to the building envelope. This picture illustrates the air tightness with tape. We used tapes in this particular instance. So all the seams on the OSB were taped, and the OSB itself was taped and sealed to structural members at the bottom and the top. So with that, now we have an airtight enclosure. Here you can see buildup starting to happen on the sides of the building. A little bit of new construction happening. And as we look down toward the ground, we dug out the sides that we had access to and insulated the basement from the outside as well. We sort of created an insulated concrete form, if you want. You can build these new from scratch that way, but we recreated that here. And in the area of the rim joist, we ended up doubling up on the foam and get extra R value in that zone. Yes, quick question.
Going back one, how is air tightness achieved at the top of the wall to the bottom of the truss?
Yeah, the question was, how is the air tightness achieved at the top of the wall and to the trusses? I'm not sure if we have a slide showing that exact detail, but we essentially air tightened to the top plate. And on the inside, we have another layer of OSB, a sealing of OSB in the building that is also sealed to the top plate. So that's where it's continuous. I think there's maybe a slide where I can point that out again. So now, yeah.
On this EPS insulation you're using on foundation, did you consider the water absorption?
Yeah, EPS is essentially inert once it's in the ground, and it doesn't really produce a liability as long as it's covered. And this is going to be covered, you'll see that in a little bit here, with a waterproofing material all the way around. So it's,
might be worth mentioning too,
yeah.
That same geofoam product, they're using it for highway fill now, so it's designed to be underground. So
Correct, and I'll just repeat that.
Absorb water though, and maybe was there a reason why you wouldn't use extruded?
Environmental impact. The question was, why would we not use extruded polystyrene? And it's mostly environmental impact on the fabrication side of it. And as Ryan pointed out, this is geofoam, so it's a product designed to work in the ground. This is typically used for bridge construction, airport runways, things like that. Yep, you can see the rim area again once it's insulated here, so layers of foam covering that very effectively. The rim usually in wood construction produces a liability, and we've sort of squashed that here by covering and overbuilding it entirely. The building was then furred out. You can see that here starting in this image with I-joists. In this case, it's a 9.5-inch I-joist cavity. These were set on top of the existing framing, and they were fastened to the existing framing, and they're essentially hung off the building. So they're not structural components. They don't support the roof or anything else. They're literally just there to support the future siding and to give us a cavity for insulation. That's their purpose. And we went to the lightest grade I-joist because they have no structural relevance here, not to overbuild that. Here's another shot of that, and you can actually see the waterproofing now on the EPS system, and that was connected at the bottom and at the top. So that's in place. There's a couple of window wells on the south side. We have a question, yes?
Is, on the existing, what I assume is a 2x4 wall, when you put your new windows and put this weight on it, what modifications do you need to make to the wall?
Yep. So the question was, what modifications were made to the original 2x4 load-bearing wall to allow for all this other work to happen for windows to get inserted and things like that? And the short answer is none. There's very little impact of what happens in that exterior cavity on the existing building itself. The improvements that were made, of course, is rectifying any framing errors or problems that were there. So if a trimmer or header was missing, or king stud or something like that, those things were repaired to make the building structurally sound. But beyond that, there wasn't any other requirement for that system. Yeah. Here's a shot of a window cavity. We used the same I-joists around the window opening to create essentially a buck condition. For those of you who are builders who know what that means, but essentially we needed to create a surface all the way around the opening where the window could actually be nailed, or in this case, screwed to. Here's a close-up, and from left to right, you're looking at the 2x4. You can see the Siga Weglove tape there, which is taping the air tightness and vapor retarder layer to the window opening itself. You can see the I-joist now next, and the I-joist was actually infilled partially with OSB sheet good, and we did that to create a point where the window could be inserted so that it's clear where the window sits. It basically denotes the exact location of the window, and that additional OSB made the flange of the web of the OSB, again, the web of the TJI stronger to give it more meat to fasten the window to. So in that first part of the I-joist where you're looking at that second layer of OSB, that's where the window was inserted in that particular zone. And then going toward the outside, you're looking at the second flange of the I-joist, you're looking at build-right, building sheathing, and then building paper and ventilated siding. Here's just another shot from a different angle. And here you can see how the windows were taped to the window opening. We now have, once the window is taped to that opening, we now have continuous air tightness from the window to the rough opening and from the rough opening to the building sheathing. So we've completed the air tightness layer all the way from the window frame onto the building envelope itself. Here's another shot of that. Here's just a view of a window from the inside in a wall, and then you can see the same thing on the outside. Now these windows are placed about, I would say 50-50, or maybe it's 60-40 in that wall cavity. They're about at the thermal center of the wall, and that makes sense. If you put them on the outside, at least in our climate zone, you expose them to colder temperatures and you risk condensation points. Also, it's outside of the weather plane. So it's not subject to the same onslaught of what you would find in a nailing flange window application. Just a couple more images here showcasing the furred out building. At this stage, we went in with a blower door for the first time and we tested. The airtight envelope was now established. All the connections were made. All the openings were filled. So we could bring in our friends from the blower door company. And they brought the right door. We've seen other projects where that wasn't the case. Please note the small blower fan. And so on this particular project, in this instance, rough-in only, we were able to achieve 0.87 air changes per hour. There it is, 267 CFM, and that compares to the 2100 when we started and 8.5. So we're at about that tenfold reduction already, and we're within the 1.0 limit of what the standard tells us where we should be. So this was a very happy day for everybody involved. It was a very exciting day, and for those of you involved in these projects, bring everybody out there on that day. There's a lot to be learned. A couple of images from that day. We ended up using a smoke machine, and you can see it's a little hazy in this picture here, to look for leaks. Even at 267 CFM, we're still looking for leaks because there may still be some that we can do away with. This image actually shows what I was talking about earlier, the ceiling. If you remember, we have roof trusses up at the very top, and we sheathed the roof truss on the underside with OSB, just like we did the wall. And we taped that OSB. That's the green tape that you're looking at in this image. And then we furred the actual ceiling down with a 2x6. And the reason why we did that is to create a cavity for lights, for electrical, for ventilation equipment, and things like that. So we created an installation cavity in the ceiling, if you want. And we have a continuous air and vapor management barrier that is up above and away from that. And we have that in the wall and in the ceiling. So if the homeowner decides to put a bunch of nails in the wall or a hook in the ceiling, they're not going to damage that layer because it is a fair distance away from the surface that they see and live in. Here are a couple of pictures of the day, and the guy on the right, that's Paul. He owns the house, and he did a lot of the work looking for holes. We pressurized the building, and then we used the theater smoke machine, and we were simply looking for that smoke to disappear or come out on the other side. And that's how you look for holes, so no rocket science here. And on a good day, you'll end up with a building full of smoke, and that tells you you've made an airtight building envelope. And I will say thank you to Ryan and Paul for making it that. It was exciting. Here's another impression of the addition, first floor addition. This is the future dining and living area. And on the right-hand side, you get a little impression of the stacks of foam that were used below grade. This is a shot that was taken in Arnie's shop, and Arnie's here today. He was the insulator on the project, and here's a nice picture of him. He was kind enough to mock up the wall system for us in his shop. When we started, there was some doubts and some questions on, can you actually dense pack a cavity of that size? And dense packing means we have to push enough cellulose into these walls to achieve 3.5 pounds per cubic foot. Did I say that right? Right on. And so we had Arnie build a few test walls, and he actually tried with different dimensions. So we had 9.5 and I think 12-inch I-joists, and we had them different spacing on center. And at the end of that day, we realized that at least Arnie, with his skill, could dense pack cavities up to 32 inches wide fairly successfully. And you can see the insole web that's used to provide a barrier while you're packing the wall. We ended up cutting a bunch of it off, and none of the insulation falls out on its own when it's dense packed. And I'm probably being as much an advocate here for cellulose insulation as anything, and that would work on any project, but it has proven to be a great material for the application. It's reasonably cheap. Here in our neck of the woods, we have access to local product. It's upcycled. It comes from newspaper waste, essentially. And so it's a great thing to use. And keeping deconstruction in mind, this building isn't going to last forever. This doesn't, unlike the foam, create a weird composite. At the end of its life cycle, somebody can cut open those cavities and simply scrape that cellulose back into a bucket and get back at the wood framing members. Here's the application on the building. Looks just like in the picture in the shop, and you can see all the walls being dense packed. Here's Arnie's crew doing that kind of work, and you can see on the building corner in the front, the sheathing's already going on and the building paper is already going on. Again, this process in general, very similar to any type of standard construction. There's just more of it. Question in the audience.
At the OSB line there on the sheeting, what was the percentage R value position of the OSB in the wall?
Oh, where the OSB actually is in the wall. in terms of how much R value is in and how much is out. So the question was, if you looked at the whole section of the wall, we have a 2x4 construction on the inside, and we have 9.5-inch I-joists on the outside. And the inside so provides about 3.5 inches of insulation. The outside provides 9.5 inches of insulation. Does that help? So you could translate that into R value at 3.5 per inch or so to what that means for those two cavities. Yeah. It was slated to be, in the end product, the inside was filled with fiberglass insulation. And I think that was done for cost and practical purposes, really. It's just a little harder to dense pack that with all the wiring and whatnot going on. And really for the model, it doesn't make any difference. The dew point doesn't shift into that interior wall. We did determine that with hydrothermal modeling. So from that standpoint, we had no problems with that change. Yeah. Here's a shot of the building with building paper going up. Again, this is very traditional construction method at this point. And you can see how it's sort of creeping up toward the windows here. And we added ventilated siding to the building. We feel that that's a best practice no matter what building you make, just to maintain moisture management and allow the product, the siding product in this case, to last longer. The building was sheathed in hardy plank and then later painted. And you can see, part of green construction is also recycling. And when you're dealing with an old building, there's lots to recycle. And you can see some of the scrap lumber that's now being ripped and used here for furring strips. And so that's another good way to recycle on the job site. I should also point out, when you look at the window, you can see the exterior window sill pan at the bottom. It's got tape on it in the front to protect it from getting scratched, but it's essentially the same color as the window. And those things are there to essentially channel the water away from the window and out away from the building. They're an integral part of the window system that's being used in this project. And in this case, these were OptiWin windows from Germany. And they're a high performance product, and they're made particularly for these applications. They offer a solar heat gain coefficient of 50%. Some of their glazing products can go higher than that, which is great for the passive solar heat gain. And at the same time, the U value, the metric U value is down in the 0.8 range, which I think that translates to what, R8 to R10, somewhere thereabouts, yeah, for the installed product. And you can compare that for local double pane product at about an R3.5 maybe. And to put it in perspective on the heat gain side, standard windows you buy in this neck of the woods have a solar heat gain coefficient of about 30%. So they let in a lot less of the sun's energy. Here's a picture of it all coming together, street facade. And as I pointed out earlier, the chimney now is a decorative element. The building was originally designed with a metal roof, and that had to be cut due to cost. But the roof is actually set up to receive a metal roof, and it has full continuous underlayment. So when the shingles are done, at that point, the homeowners can put the metal roof on it. So we're essentially shifting that back the life cycle of one set of shingles to save some cost here on day one. Here's a couple of exterior details, and this is probably, again, no different from standard construction. This building has a fairly ornate window detail. It sort of hints back at the day and age that it was originally built in. You could see it starting to come together here. Maybe I'll pause on this slide for just a second and talk a little bit about cost. And we could talk about cost on a project like this for an hour easily, but what I can tell you is that the original budget for this was $200,000. And it was clear that that's challenging because so many things were replaced. It was completely rebuilt inside out. We also had a lot of discussion about, is that really worth it? I can tell you that it is worth it. If you had built a house that size new to that same standard, it would have cost probably $100,000 in excess of what it costs to retrofit it. So while this is a big undertaking, financially speaking, it can be well worth it or cheaper than building new. But it is a big undertaking, and there's really no way to talk your way out of that. This is not cheap. The certainty you get with something like this is that this is the last retrofit for that building. You're not going to go back and add more insulation or better windows to this building. And we can reasonably say that with some foresight. And the products and materials and installations chosen are all selected for a long life cycle. So we want to really get this building to a point where that need is significantly reduced. The final cost, I don't know if it's in yet altogether. I think street market value, had you hired any builder to complete the whole project for you, it may be closer to $300,000. The homeowner did a lot of work themselves. They had a little bit of a marketing campaign going on, and they got some generous gifts and donations that helped make this possible. But I will say in some areas, they also maybe went beyond the standard of what you would expect in this neighborhood and in this house. So there are some things that ended up being nicer than you would normally have. And so it's a little bit of an unknown. I think we'll do a little bit more work in researching that and getting some clarity on that. But just to set an expectation for where it goes when you embark on a journey like this.
Is that foundation insulation then exposed there with waterproofing? Is that like eaves and waterproofing?
Correct. The question was, is the waterproofing on the foundation, is that an eaves type product? And it is, yes. It's a Stoll product called Flexol, and it's an exterior insulation finish system that we used all the way down to the footing, and that is exposed in this particular area. Correct. One thing maybe to note here too is you can see successively toward the rear of the building, especially on the second floor, our windows got a little bigger. So in the newer part of the home, we sort of broke with the tradition of the small window that this building was set up originally and expanded to larger units. The view from there is great. It's across people's yards because we extrude it to the back. We get better solar heat gain input at those locations, and just wanted to make sure that we bump up the daylighting a little bit for the homeowners. In the front, though, we stuck with all the rough openings that were there. A couple of slides here on the mechanical system. This is the ventilator. You saw it in a schematic earlier. That's the actual machine. It's made by a company called Paul, locally sold in the US through Zender and their network. They were hoping to be here today. They couldn't make it work. Their cards are outside if you want to grab them. They supply these kinds of systems. There are 2 to 3 vendors in the marketplace that we typically choose from. And their product here delivers a 93% heat recovery rate, and that's top of the pops in residential product that is available right now. So this is literally the best ventilator that money can buy right now. To the right, the metal box that you're looking at is a manifold and sound attenuation box. So it kills telephone effect from one room to the other and noise from the machine to the rooms. And on the right-hand side, you can see the little ducts, which are the home run supplies. Here's just a quick shot of a air supply duct or pipe. We have some of that product floating around here for those of you in the room. You can touch that later. But essentially what that is just an insulated duct. And it brings air in from the outside and expels it to the outside. And so instead of making a duct and then insulating it, the insulation is the duct, if that makes sense. You can see all the pipes supplying in each individual room in this next slide. Home run system, as I pointed out, they're 3-inch flex ducts. And again, there are a couple of vendors that sell this kind of thing. And it's so simple to install. The homeowner can do it. Paul can testify to it. And I actually can too, because I put one of those in my own house. So if I can do it, you can do it.
So Tim,
yes.
The reason why piping is so small is because you're not having to heat.
That is correct.
Push heat through the duct.
That's correct. The question was, they can be so small because you're only ventilating, and that's exactly right. You're not heating, you're not cooling, you're just ventilating with the system. The airflow in a building like this is somewhere around 200 cubic meters an hour. What is that, Philip? 120 CFMs. Okay, so for the whole house ventilation. Yeah, I apologize for my metric mind. Here's a vertical run. One of the things that we did on the architectural design of things is we created a vertical supply wall, if you want, that is continuous through the entire building. It goes from the basement all the way up, and all the plumbing, heating supply runs, major arteries for electrical, plumbing, you name it, including the ventilation lines, go up and down in that cavity. So that means short runs, and it means you know where this stuff is. It's only in one location. Here's the outlet for one of those supplies. And you can see this particular system here goes back to sheet metal, and the sort of pin or nozzle that's pointing down will later be trimmed to the ceiling and then fitted with a diffuser. So that's really all it is. Here's the boiler. That's an on-demand unit, condensing, modulating. It's about as good of a boiler as you can buy right now in the mid-90s for efficiency. And again, that system was already there, so we leveraged that and continue to use that in the finished product. It's sitting here on one wall, and it's basically generating heat. That's not fully finished, so not all the pipes are insulated. And it goes to the same wall that I talked about, the supply wall, and this is sort of our load center for hot water, if you wish. Now, I will say that in most passive houses, when you build new, you're not going to have this at all. The mechanical system is so reduced that you likely won't end up with this. But in this case, because we're weaving in existing and new stuff, it made sense to hold on to some of that infrastructure and just make it better. And I suppose it helped that Uponor became a sponsor on the project, because there's a lot of nice Uponor product in here now. And you can see, for instance, on the left-hand side, that vertical tree that you're looking at, that is a hot and cold water manifold. So in this house, all the water supplies are home run. So the homeowner can actually shut off each water device from this tree. And that's a unique system, not that Uponor wouldn't sell it to anybody. I'm not saying that, but you don't have to have this in a passive house or in a retrofit. It's just here because there was an opportunity to put it in this project. Also, the in-floor heat. The heat load on this project is about 3,700 watts. That's about 3 hair dryers going at the same time. They will heat the house on the coldest day of the year. So to have a full-blown in-floor heating system to deliver that is somewhat overkill. But again, it was there, it existed, and so tying into that infrastructure made a lot of sense. And for comfort, it is nice to have the warmer floors, especially in the bathrooms. So on the right-hand side, all that infrastructure caters to that in-floor system alone. The tree in the middle there is for hot water, and then you have a couple of expansion tanks and heat exchangers, and that's really all you're looking at. So don't let that overwhelm you. The schematic that I showed earlier is true, that is the system. Here's an image that we took just a week or so ago. So the homeowners are still chipping away at it. I can't give you the completely finished and final product. This is as good as it gets right now, and they continue to work on it. Here are a couple of interior shots that we took. You can see the living kitchen come to life with a big center island. The structural column here will later be enclosed. We're looking at it from the addition, living room, dining room. Now, a couple of impressions from the bathrooms. You can see the old trim being recreated. So we have essentially, 19th century trim and a 21st century window meet each other there. A couple of impressions here of the nice tile work that's going in. And air tightness. Oh yeah, the big one. So we just did the blower door test a couple of days ago for the certification. Again, limit is 1.0. We were at 0.87 on the rough-in, and we managed to get it down to 0.65. So not a huge improvement, but enough of an improvement to basically meet the 0.6 air change limit for a passive house, just a little over. But 1.0 was our goal, so we did a lot better than we all thought we would. So it is possible in a retrofit scenario in wood construction to make a building that is this airtight. For those of you who are geeks, here are the numbers. Specific heat demand, that is the energy that it takes to heat the house. We're heating dominated here, so that's what we look at. If you were in Florida, this would be for cooling. We have a limit of 25 if we want to certify the whole house based on the limit. Currently, the model sits at 24.5, and it was designed to come in at the limit. We didn't want to overbuild it. The heating load itself, that's what I was talking about earlier, to heat the building on the coldest day of the year, 3.78 kilowatts or 12.9 kilo BTUs. That may translate to 35 of your closest friends and 120 candles or something like that. Air tightness, I just showed you 0.65, and the specific primary energy demand, this is now again all of the energy that flows through this building accounted for at the source, so at the natural gas source and the electricity plant, comes out to 111 kilowatt hours per square meter year, or 35.2 kilo BTUs, and our limit for this project was 130. And for those of you who are passive house experts, you'll recognize that that's above 120, which is a limit in new construction. The reason why that's okay is because in a retrofit scenario, you get an allowance over the 120 based on where your specific heat demand is. And I'll just leave it at that because that's very detailed for Passive House folks. So what are we thinking when we do this? Here's the last laundry list, I think. Structure, yes. Weather barrier, I've shown you that. It's all taped up and sealed up. Insulation, I think it's fair to say we have enough. Air tightness, yes. Moisture management comes out of the assemblies and the choices of product that we embedded. Ventilation and air quality coming out of the ventilation equipment, obviously, and that's in there. Comfort, I would suggest that that is one of the single biggest improvements beyond the architectural improvement in this project. They should not have a problem heating it above 64 degrees on the coldest day of the year. And the interior surface of exterior walls should be within a couple of degrees of the room temperature, making it very cozy. Daylight, we tried where we could. You saw some of the bigger windows. The areas that we controlled, we were able to daylight better. Durability, really with the products and assemblies that we inserted, we want to get to 50-year life cycle on the major components, certainly 100-year life for the building itself, given where it's at right now. You know as well as I do that every bit of equipment has a different life cycle, but the windows are one of the bigger components here that play a role, and we feel that that's a 50-year product. The mechanical equipment may not quite live up to that, but then again, it never does, and that doesn't change in this paradigm. But 50 to 100-year life cycle is certainly what we designed this for. Design, you know, the homeowners love it. I think it fits well within the neighborhood. You haven't been there, you can drive by if you're local here and be the judge of that, but we try to be respectful of where it is and what it is. Life cycle cost, we didn't touch on that quite as much, but you know, obviously beyond your initial investment, there is a significant change in now owning a building like this. It starts with the utility cost being dramatically lower, and it extends through the maintenance cost. Because the assemblies were carefully chosen and quality product was installed in a quality manner, you extend the shelf life and the maintenance cycle of a lot of the building systems. And even just an extension by a factor of 2 is a significant reduction when you look at owning a building 30, 40, 50 years. And if you know you like where you are, and if you're building an asset for your family, then you may be concerned with those implications down the line. So really, part of this is really to look at life cycle cost. And another point I want to make is that if you invest $200,000 in a retrofit like that, it's not the fact, or what's important here is you haven't invested $200,000 in the Passive House upgrade, because this building would have received a remodel and an addition anyways. And I think Ryan would probably agree with me that, you know, somewhere between $150,000 to $200,000 would have been a standard local retrofit project. So the fact that we're somewhere between 200 and 300 with the unknowns of some of the sweat equity and the sponsorship in that bracket between 200 and 300. So there is an upcharge going to this that produces a significant return on the flip side, but it doesn't account for the entire cost of the project. It's probably clear to all of you listening, but you know, what I find is if I don't say it, people take away, oh, the whole, you know, just because it's a Passive House, it costs 300 grand. No. You know, a lot of the stuff that was done here, the shot infrastructure, the reframing, all the repairs, the fact that we added, none of these things had anything to do with that. And arguably, the bulk of the cost was not in the Passive House upgrade. That is incremental cost. And, you know, typically, if we have to put a number on it, we gauge that there's maybe a 10 to 20% increase over the standard project to get to this level of performance. So on this project, if I take that math, you know, it may be 40 or 50 grand extra to update it from something that would have met Minnesota building code to what it is today. And you can make a calculation on the return of that investment over the next 15, 20, 30 years. In new construction, we have a better handle on it because we've run more financial models. And in our local climate, we found the break-even point at just over 14 years. So I just want to give you some expectation of where that is.
Hey, Tim.
Yes.
Regarding ventilation, can it be variable and controlled? You know, if you exhaust air, how is it reheated and pressure intake?
Right. So the ventilation system does not heat per se. It's just based on heat recovery. And again, the ventilator has a 93% heat recovery potential, but there is a preheating element, which is just straight up electric resistance on the air intake side that kicks in under certain circumstances to keep the machine from freezing up in the winter. This particular machine can go down to -5F, if I remember right, without freezing up. And then once temperatures on the intake side go below that, that backup unit is kicking in to maintain that envelope so the machine won't freeze up. You're talking literally hours over the case of the year, at least according to the model. Now, Zender is looking at monitoring that system on this particular house to find out, how often is it really kicking in? What is our real life performance? There are not many of these systems around yet, but I'm sorry?
Does it vary, the ventilation?
Oh, the rate of ventilation can vary. All ventilation equipment is usually 2 or 3 stage. And you can program these stages. There is a design ventilation rate that's geared toward healthy air change, 0.3 an hour, and that's our standard. There's typically a high mode that can be triggered by air pollution if it's automated, or by trigger switch in a bathroom, for instance. And there can be an away mode or a low mode for when you're going on vacation or you're not there during the day, where it may ramp down, because you don't need to ventilate the house if you're not there, because you're ventilating ultimately for people and not for the structure. So those are the 3 settings, and the controls that come with that type of equipment can usually be set up a number of different ways. They can be programmed like a thermostat to do that, so you can set your own program, or they can be automated based on air quality control. So those are your options essentially, and that's homeowner choice. Or you can leave it at 1, 2, 3, and that's all you do. You just set it manually. Last couple of points here, just environmental impact. You saw with the choice of materials that we brought here that we're really trying to reduce the environmental impact of the project. We're working with wood-based products, with cellulose as best as we can on the insulation, and so we are concerned with that. And deconstructibility, I mentioned it a couple of times throughout. I think we're on a finite planet with finite resources, so we do have to look at where do the resources of the future come from. And I think we're already at a point where if you're deconstructing a home, most of that ends up being used as something again. So we're already recycling existing buildings now, and we have to keep that in mind when we make new assemblies. So that's what we call the holistic approach. And these are the guys that we did that for, and that did a lot of the work, frankly. And so my thanks goes to them for enabling that and allowing us to do the work that we do. And I'll close there for now. All right. Questions? Yeah.
Did you ventilate the attic?
Yes. The question was, did we ventilate the attic? And yes, we did. The attic is fully ventilated through the soffit, air intake all the way around, and it's a hip roof, so that's very easy to do, as a ridge vent at the top. And on the sides, at the energy heel, where the insulation would sort of fill those cavities, we install vent chutes. So there's a vent chute that allows that air to come in through the soffit, through the insulation layer, and then exit out the top.
So nothing outside of what the code requires at this time? You didn't have
No.
to do a variance or anything?
No, there's no, on this project, there isn't a variance or any sort of code related issue. The only, I think, issue, if anything, that came up during the project was that the house sat too close to the neighbor's lot line on the north. And the north wall, I didn't get into that in detail, but one wall we actually had to build in rather than out. Yeah. We ended up, and just to sort of complete that story, on this particular project, there are 3 different slab conditions, 3 different below grade wall assemblies, and 3 different above grade wall assemblies beyond the basic setup that I showed you. And they're all in response to individual conditions that we had to deal with that we couldn't make go away.
Do you do anything special for plumbing vents?
Yeah, the question was, what do we do for plumbing vents? Minnesota, as far as I understand, is one of only 2 states left in the country that require a plumbing vent above roof. So if we build outside of Minnesota, that's easy. We use an air admittance valve. In Minnesota, and especially in Minneapolis, they won't let us do that, so we insulate the stack. Yeah. And that's really all we can do. And since that was in the wet wall, or in that installation wall that I showed you, that wall was entirely filled with insulation on both sides to also eliminate noises from water, wastewater, you name it.
Did you do any radon venting as well?
The question was about radon venting, and the short answer is no. Other than air tightening the slab system at the bottom, It's not required in retrofits, and that doesn't mean that we wouldn't do it, because I think it's good practice. On this project, it just was, I would say, nothing's ever impossible. It was totally not feasible, simply because we had existing slab on grade areas that, and we were so close to the neighbor's lot line. Had we dug it out on those sites, we would have been digging a hole in the neighbor's yard. And so there, at some point, you got to draw the line. And an interior depressurization system, as you may imagine, doesn't work on an airtight building. So
You're probably getting enough air circulation where it's irrelevant anyway.
that's true. So the comment was made that with the mechanical ventilation, we're mitigating through dilution, and that's certainly true. So if radon were taken on, the other good news here is that a radon test was performed with the old house. And I think it came in right on the line. What is it, 0.4 microns or something like that. And so it you know, it's at the point where you could live with it, or you could choose to do a little something, but it wasn't anywhere near alarming. And so that's the great thing in retrofitting. You can actually test it, because in new construction there's really no test to find out what's radon like on my site. And so we were able to leverage that, and we knew there wasn't big exposure on site. But it's a good point. It's about time to give the homeowner another test and see where they're at now. Yeah, next question.
During the design phase, as you were drawing, did you ever stop and consider, I should just take this building down and start?
Yeah, a question was raised during the design if we ever thought it should be torn down. Yeah. So I think Ryan, and feel free to come up, Ryan, and answer some of these questions too. Ryan, the builder, is here in the audience.
Just with the challenges of the stair you referenced.
Right. No, it's a perfectly good question. I thrive on challenge personally. I love doing this kind of stuff. And I can tell you that there were many more hours in this project than the client or anybody else ever paid for, simply because we like the work that we do, and we do want to make it work. As I told you before, I've done a number of these projects, maybe not to the EnerPHit level, but in that realm. And on every project, in hindsight, we found that it was cheaper to retrofit it than to build it new. On every single one. On this type scale, it's usually ends up being probably $100,000 advantage over the new build. So there is inherent value in that old structure. It exists. The thing is, when you nuke a building, you have to take the basement out, you have to backfill, you have to start excavating again. For structural reasons, you can't really leverage a hole, it's not safe. And so you're really starting over. So there's a lot of costs that you incur by taking a house out and starting over. So if the structure will bear it, it does make sense. It is frustrating when you're on your third or fourth assembly, different wall system, and you just wish, why can't they all be the same? Because nobody wants to pay you for another wall. But that, I think that's part of what we do. That's what, if we engage in that process, we have to respond appropriately. And I'll let Ryan answer for what he's doing as a builder. I don't know your level of frustration.
Yeah, it's very frustrating. I mean, it's obviously not fun work either when you're tearing everything apart. It's messy, it's difficult, and everything else. But there were, looking back at it, that question was one of the biggest ones in our minds and asked a lot, I think, every day. But I went back, started monkeying around with the budget again. What if we did tear it down? And it is significantly more expensive. There's a lot of other issues that would come up, especially being in Minneapolis, that, zoning setbacks, shoring a hole, complying with, new ordinances versus existing, it would be very difficult.
So it's still considered a remodel.
It is considered a remodel. And that was a good point you made with the zoning, being that it was not in compliance on one side. They could not rebuild the house in the same location. We would have had to move it on site, and which would have had implications for their solar heat gain and what they look at on the south side. And
the city would have actually made us go in, cut the sewer and water line off at the street as well. We'd have to replace that again. So there's a lot of redundant costs that would be added onto it that really weren't necessary if we keep just even the foundation in place. And if you strip the house down to the foundation itself, at least you're still saving something of, pretty significant cost.
How about out of plumb and true and level? Is that a challenge?
We had a lot of that.
the question was how to plumb and level and true. And
he had some pictures of that knee wall structure that we added above to raise the wall. And, originally when we were planning it, okay, well, we'll just add on a knee wall. But there are not two studs in there that are the same length, so it was a challenge.
So there's some cost factor there that doesn't really impact.
And it would have been the case in any remodeling, though. Yeah, anytime we remodel an older homes, it's pretty much a given. Things are not necessarily plumb or level or straight. Headers are usually not there. Insulation's not there. So, I mean, a lot of this stuff really was just caused by the fact that it was such an old home that even if you just did a code remodel, we would have been down to the bare bones like we were. So, you know, I think the increased insulation and the I-joist costs were probably the only major changes. Could actually save some on the heating system, so
Yeah.
that balances it out.
Yeah, question in the
Were
back.
there any thermal images taken of the envelope?
Question was, do thermal images on the envelope? Short answer is no, not since it's been done. You know, the building is substantially complete, if you want to call it that, but it's not fully complete. And so we went back, we did the blower door test the other day, but, you know, again, you have to keep in mind a lot of this is based on donations and goodwill. We have the good fortune that the Minneapolis blower door is manufactured here in town by the Energy Conservatory, and they're good friends of ours, and they will come and they test our buildings right now. And we, you know, we have great access to that, but not unlimited access. So we were grateful that that got done. But right now, there's no. I'm sure the homeowner is not interested in funding thermal imagery of the building, and I don't know that we're in a place where we can do that. We've already leveraged a lot of what we, you know, needed to do here to get this right. We're going through the certification right now with the PHAMSP House Institute in Germany. Maybe for those of you interested in that infrastructure too, the EnerPHit is a newer standard, so that currently can only be certified by the German Institute and I think 7 of their outposts, and the American PHAMSP House Institute is not one of them. So we have to have it certified there. And that's something that we're donating to the cause. The infrared imagery is not required to certify any passive house because the assumption is with the blower door testing and the leakage search that we perform that we're, you know, reasonably in safe territory there where we don't have bypasses. I wouldn't say that it's not of interest. And if you or anybody in the room had access to that, I think we'd all be open to doing a session out there. Obviously, right now would be a bad time of year because the temperatures are too close nearby. But in a couple of 3 months or something, we could certainly go back out there and do that as well. I'm sure you'd find open ears, but there's nobody to fund that kind of work right now. And that's, you know, I'll put that out there too, because I know there's a few people listening here outside on the webinar. You know, the thing is that in the passive house community, especially the geeks that, you know, like us, that really dig into this stuff, we'd love to have all that. And we want the house fully monitored. We want to know where's the dew point in the wall and all these other things. And the fact of the matter is that these are people's houses. We can't make every single one a lab. You know, we've done that with one house already where it's sort of a half a lab and it's fairly well instrumented. The bio house that you see up on our wall here is fully instrumented. And I can actually, from here, I can turn the ventilator off if I care to while they're in it and play with the folks. You know, that's all great. But the reality of it is that we can't do that on every project. And it also goes to the sponsorship piece, since there was some sponsorship and marketing campaign on this. What we found is this is still new enough where people come out of the woodworks and they want to donate, and it's very tempting. But I will say, just as a word of caution, and I told Desiree and Paul that, and we all realize that there's nothing ever free in this world. When you engage in that kind of a process, be advised that it doesn't necessarily save you money. It may give you more house for your money, is what it may do. But you're still on the hook to pay for the project, and they need to see that. So you're still initiating and on the hook for the cost. And also they may dictate some of the stuff that you need to put in, whether you want it or not. And then you deal with that. I think case in point, expensive tile. It's great to get it donated, but then you need a real good tile setter to put it in, and that's your cost. So just keep that in mind. And again, we all love to do firsts, and we love to do prototypes and pilots and lighthouses, but we have to realize that these are life projects for real people, and that's why I always put the slide of the family in. That's really what it's about at the end of the day. It has to work for them. Right.
So the certification is really to verify in the future when you sell it that it's well built.
Yes, question was certification basically guarantees in the future that it met the standard. And I think that's true. Any certification, be it LEED or Green Star or something like that, all it does is you have a third party look over all your documentation and ensure that it was built to a certain spec. You could say that, you know, the city inspection does the same thing. It guarantees, or we would hope so,
Yeah.
that the building was built to the local building ordinance, and that's worth something as well. So it's basically the same process. You just get another eye on it. And, you know, passive house like LEED or Green Star is more thorough there. I mean, the amount of information you need to accumulate here to go through certification is pretty significant. But the nice thing is, once you do it, you can put that on a memory stick and you can give it to the homeowner. It can stay with the project. You could print it out if you believe in paper, and then you have it. And you can, you know, indefinitely testify to the things that were done and how they were done. And again, if somebody were to go back and look at some of this stuff and need to make changes to it, they would know what they're dealing with. So I think there's an added value in the documentation that goes beyond the simple certification. Right. Question over here. Yeah.
Yeah. What's the square footage of the addition again?
The square footage of the addition was 800, and it was on 2 floors. So the house had 1,200 on 3 floors, and it wasn't quite even because the basement's really small. And then the addition was 400 2 times.
So total about 2,000 square feet.
Now it's 2,000 square feet finished. Correct.
That's exterior envelope rather than TFA.
That's the net square footage usable.
Okay.
I can't tell you off the top of my head what the gross square footage is,
Okay.
but the walls are about 1.5 feet, so you'd have to add that to the circumference there. It may be 20% more, so it may be 2,400 gross or something like that. Yeah. So you could now go and try to get dollars per square foot based on that, and you'd end up somewhere around $100 probably per gross square foot. I don't know if that helps anybody. Yeah, question in the back. Did you have? Oh, sorry. Don't mean to put you on. There's a question.
You mentioned variety of wall types and the north wall height inside versus outside, and that becomes messy details where the vapor barrier is, where the air barrier is.
It's never messy. We know exactly where the air barrier is. That's why people hire me, is because I know where the air barrier is. I'm sorry. What was the question?
It's the transition between the two wall systems and everything. And
yes, that's another detail that nobody wants to draw and look at. No, yeah. No.
At what point do you say we can't do this? We just do it and try it.
No, we do it. I mean, again, the way this works is divide and conquer. So now you have a new wall, and then you have these 2 walls meet. So there's another detail, and you know, I could rip on some of the work I've seen done in other places I've worked where, you know, I think the motto of the company was, you know, let's draw all the details except the ones that show how these things come together, right? You've seen the 5-page set, and that's it for an entire building. You know, we end up with, I forget what it was on this project, 20, 30 sheets or something like that.
It's a thick roll.
Yes. You just divide and conquer. You pick these things out one at a time and you solve them. And there's always a solution. And again, in wood construction, more easily so than maybe in some others. Masonry construction can be particularly challenging, especially if you have to jog outside to inside, because you inevitably end up with an area that you can't penetrate with air tightness, with insulation values. So thankfully that wasn't so much of an issue here. But yeah, what can I tell you? It's just, I mean, not to boast our own services, but it is years of experience and looking at this crap, for lack of a better term, you know, these existing conditions in the field. I've seen tons of these things, and I've tried to solve them many different ways, and getting feedback from people like Ryan is crucial.
Yeah,
you know,
having everybody on the same page is probably one of the most critical elements of it too, because if we find stuff and we just blow past it, it's obviously not going to perform. He can't design anything, and we can't fix the problem. So, you know, really what works best is, you know, identifying the problems and coming up with a solution. And we found several problems throughout, but I mean, coming up with the solution really wasn't all that difficult, you know, having the right people involved. Seemed like it.
So you know, I could illustrate that with an example. Early on, when we dug out the basement slab, you know, the way that we do a drawing, of course, that wall is sitting on a perfectly square footing, right? But in 1935, You know, if you were lucky to have a footing, the way a footing was built is somebody dug a trench by hand and then flooded it with concrete. So by the time you unearth that, that is more of a balloon sort of sphere.
It's a very odd shape. It's
So, you know, how do you solve that? So what happened was, as soon as they uncovered that, you know, it was essentially the builder, the homeowner, the structural engineer, and us trading, you know, bumwat sketches. You know, this is kind of what we found. This is where we need to be with the new stuff, and then what happens in between. And there is a gray area. And in this case, I think the gray area was filled with more concrete to square it off, literally. So, you know, it's sometimes, you know, we try to preempt as much as we can, but at the same time, you have to draw a line, and some of these things you can only solve as they come up. And so when you engage in a project like that, you have to be ready to be sitting there and take that call, and then on the fly re-engineer that thing to do it what you actually assumed it would do. And there were a couple of instances maybe where we did that, not a whole lot. Yeah.
So as a result from that, you probably need a much larger contingency and a much more reasonable owner.
On the architectural side?
Yeah, and even the building side.
That goes to the
I mean,
model.
I guess it would. It depends. I mean, as a remodeler and working on older homes, especially in that particular neighborhood, I've done quite a few additions, and you know, there's a certain amount of contingency that you need there, but I don't think that the conditions that we found caused huge cost increases. You know, not that I can think of. I mean, they're not really out of the ordinary, I would say.
Yeah, and I mean, from the architectural side, I'm sort of lacking comparison. I suppose I haven't worked at enough different firms to really know what the next architect would charge for this. I know what I would charge for it, and I think, you know, retrofits and remodels are inherently difficult, and typically, especially on lower budget projects, the fees tend to be at a higher percentage. We don't bill on a percentage base. We try to bill based on effort. You know, we bill hourly sometimes, but we try to generate a scope based on effort of what we see the task to be, and so that's how we approach this. And if Paul were here, he would probably say that he, you know, he reached his limit on what he would want to pay for design services. And you know, I think we're good friends. We can look each other in the eye, and I think we're all okay with that. I think he reached his limit, and we reached our limit with additional work that we could, you know, throw at that project to get it to where it is. The thing is, you know, this is an evolutionary process, and that this is somewhat of a building revolution that we're involved in here. And so what it takes on the design side is an owner who is willing and able, and it takes a designer who's willing and able. And if we find each other, then fine, we can engage in this. And I think, you know, the more of this that we do, the more we can wrap our head around and maybe leverage some of the past work that's been done and use precedent. And if we, you know, have the good fortune of engaging in projects with the same team, bringing builder back in the project, then we can further bring efficiencies to it and make it more palatable. But at the same time, we all have to acknowledge, you know, this is sort of a one-of-a-kind thing. There is not a lot of precedent for this kind of work. And you know, I'm thankful that we can get it done at all, and that there are people who allow us to go down that path. And at the end of the day, I'm not going to tell you what my fee was. You know, maybe Paul he can feel free to share that, but I think it was reasonable. I think that it's thinkable that the next architect just doing a retrofit addition, normal stuff, would have charged the same money. I don't think that it's beyond that. That's from my experience. And I see that on our new construction projects too, that if you integrate this into your design process deep enough, then you can essentially deliver a better product for a lower price, for, you know, with the risk of upsetting some of my colleagues now. But the thing is that, you know, if that's how you approach it from day one, and you try to make different assemblies, and you know about air tightness and all these other things, it's not an afterthought. You're not hiring a consultant to bring that in. Then arguably, again, it doesn't have to cost a whole lot more. And I would take a guess and say for Ryan too, as he pointed out earlier, the additional cost, yeah, there were those eye joists, more insulation, but the windows were a little bit more expensive. But other than that, you know, everything else was kind of the same. And so I would like to think that the concept is really what's important here. You're fundamentally approaching the project in a different way. And you're trying to use the same resources that would have been thrown at the project anyways in a slightly different way. And
Yeah,
you
I
do
think-
that first before you add anything else into it.
I think in this particular project, what's kind of deceiving about it is that people see it and, oh my gosh, you had to tear the whole thing apart just to do the passive house retrofit. But to do any addition on this house, it would have been pretty much down to bare bones no matter what, because it was in very poor condition.
Yeah, the
structurally.
roof was not
I mean, it was-
sustainable. We tried early designs to add on to the roof, and we went through that with a structural engineer, and there was no use.
Yeah,
That
and the
was
ceilings
not
were
the-
low, and
No.
that they created that slope ceiling with no room for insulate. It was just
Yeah.
no options.
As far as the building code in the city, did you run into any problems with them, or?
We didn't. Paul ran into his fair share, but that was not really because of the design of what we were building. It was just because he wanted to do work himself, and they didn't feel that he should be allowed to. So they gave him a lot of resistance on his mechanical system and his. One, for example, that they really got upset with is he needed a furnace. He didn't have a furnace identified in the plans, and he needed to pull a permit for a heating system. And he said, "Well, it's my water heater," and they didn't accept that answer. So that
So
was a
then-
bit of a battle.
So did he end up losing that battle then?
He did eventually get them to come around, but it took a lot of work, a lot of time, a lot of phone calls, a lot of contact back to manufacturers to get support information and bring that back to the code officials. And they're slow to change. They're very slow to change. So it took him a lot of time.
Yeah, but it's a unique setup, certainly, when you have a homeowner who is essentially acting GC. I mean, in the
Yeah,
beginning, you
yep.
guys partnered, and now he really owns it. And
Yep.
he did all of it himself there. There's one question here that I want to weave in real quick from the web people, and that was just if there would be tours. And so if you're local here, you can stop by. The homeowners are usually open to that. You can ring them up, you can send them an email and ask for that. I don't know that they have any tours scheduled, but in the past they've been very open to having people visit and come in and see it. And at this point, you saw where it's at. It's partially completed on the inside, so you won't be able to see a lot of that insulation and that business anymore. It's really about finishes now.
Where is the house?
It's on 56th and Bloomington in South Minneapolis. It's virtually the last row, really, before you get to the airport area. So it's that's maybe another point worth making, is that when you insulate a building like that and you make it airtight and put these windows in it, that for the airport noise, that is tremendous when you're in there.
Yeah.
When we were doing the blower door test the other day, the thing is, when you're at the front door and you're chatting with somebody, every time an airplane comes overhead, you got to pause. That's how loud it is. I mean, you can literally wave at people when they're going by. And so in this case, we were inside, and I didn't notice it until I went back out. I don't think I heard a single airplane inside the house the entire time we were there.
No, when we were doing the smoke test,
Yeah.
We couldn't talk to each other really through the windows, and it was uninsulated at that point. So
Oh, on the first one, yeah, right, yeah,
the
true.
rough end.
Yeah, so that's substantial. Let's go back there, and then you, Joe.
What was the duration of the project? Schedule-wise?
Right, duration of the project. The design portion of it, I'm doing this from memory right now, but I want to say that was a little over a half year or so, off and on. And that's often driven by, homeowner availability, our availability, and all that. So that's not necessarily indicative of anything. If it had been 9 months, that wouldn't be unusual. And then once it went into construction, I think they had a sort of a thought that in 4 months they could complete this project. And I think if Ryan had been hired as a crew to do this project with subs and everything the normal way, I think that's maybe real. Maybe 4 to 6 months is real.
Yeah.
They're coming up on what? No, is it a year?
Yeah, it's been about a year. They started, I believe it was right after 4th of July. They broke ground on demolition, but I think he spent a total of a month in 105-degree heat indexes, tearing stucco off, doing interior demo, and just ripping the house apart. And then they continued that while we started framing. So when did we? I mean, they're living in the house now, but it took them all through the winter basically, because then once structure was complete and it was insulated, we worked on the exterior, wrapped that up, and then it's been kind of slow going since, because it's a lot. It's a lot for one person to take on.
Yeah, and it is literally a one-person job. And he did take some time off. I think there were probably 2 months or so over the changeover of the year, 2011, 2012, where he needed to take some time off the whole thing.
Yeah.
And it literally made no progress whatsoever. Yeah.
Mental break.
Mental break. Yeah, he did. I don't know, for those of you who saw the newspaper article, he said he was ready for asylum by the time this project's done. Yeah, if you want to change your appearance too, and I don't know if Paul's listening or not, but he did, his physical appearance was changed by this project, and forever probably will be. He lost a lot of weight.
But that can go for any.
Not that he was ever
project,
big to begin with. Yeah. So that's true, and I've had that experience on my own house as much as anything, so I can testify to that. So that's a whole nother facet of this project, is doing part of this yourself and weaving yourself in and out of it, and the repercussions of that. Yeah. Joe.
I think on the website link for the MinnePHit House, it says October 1st, but I can't tell if that's last year's tour, building tour. Or
Yeah, from the question is about a tour that's posted on the website, and my thinking is that website hasn't been updated in a while. I think that's just falling off a cliff because it's more important to get the house done. I do see occasional Twitter posts and Facebook entries, and again, you could drive by to check on the progress. I would hope that at some point it's complete enough where we can go through there and get some more photos and maybe do a little diary of that. But right now it's sort of in between. It's not finished enough yet. Yeah.
Tim, just a quick question about cooling the house.
Yeah.
So you notice that I haven't run away yet after hearing all this.
Yeah, he's thinking about doing something like that.
How do you cool? Do you then remove the furnace? Do you remove the AC? Or how do you tie in what's pre-existing with?
Right. So, there are two schools of thought here. Maintaining existing infrastructure when it makes sense and when it can be downsized to work with the loads you end up with, or removing and replacing infrastructure. In this particular house, the air conditioning system was very small, and it was basically run through the attic. I showed that earlier, so it was a huge liability. And when you build a new roof, that thing just disappeared. So that was no longer an option. When you end up with a building at that level of performance, point source heat and cooling can be acceptable for the whole house. So you're no longer concerned with getting an outlet into each room, because the idea again is coasting. You condition the building at a comfortable temperature and you coast through swings outside. So you're not really dealing with latent loads where you're all of a sudden trying to cool the house down from 90. You're just trying to maintain 70 as it warms up in the summer outside. And with the help of the ventilation system, you have a complete changeover of the air and movement throughout the home at all times. And that helps too. So in this case, this building will be cooled with a single point source mini split air conditioner that resides on the second floor in a common area. And that's it. And that unit could theoretically even be used to heat the building. But since we have natural gas heating here, electric heating is maybe not the best idea, but it could. And dehumidification is dealt with in the same way. That unit can be used as a dehumidifier only, or it can cool and dehumidify at the same time. And you got to keep in mind just this: the infiltration, is cut out by so much, so that infiltration of humidity and heat, because the building is so airtight, is reduced by a huge margin. So again, your loads are really small, where that approach can be very acceptable.
He did actually heat the house with space heaters in the winter, and I mean, to any of us that are experienced with normal construction, I mean, we just figured that's going to be pointless, but it actually worked quite well. And the thing that we were surprised by is even before the ventilator was turned on, how well the heat was, sort of evened out throughout the house, even with literally just one of those oil-filled Target space heaters sitting in the middle of the room. And the bedrooms were probably a couple degrees cooler, but really not that bad considering there was nothing circulating in the air.
And I will say it was missing all of the interior insulation at that point. It only had the exterior insulation at that point.
So. And the window wrap as well. So there was, but it works well.
Yeah, so that's usually the easier part of the equation. I think, and I can be honest about it because I've experienced it in the passive house in the woods, which was new construction that we built for somebody where we don't have active cooling. You can heat up that home from the inside. Again, if you bring a lot of people in, you do a lot of heavy cooking and you close it off and it's maybe warm to begin with, then at that point, you will need maybe an active cooling mechanism to maintain a comfort envelope. Although I will say for a house that doesn't have active cooling, it topped out, and we've had a month of above 90-degree temperatures with high humidity. It topped out at just over 80 degrees and a 50% relative humidity. I personally would find that unacceptable. I would want that to be no more than 78. But for some people, that's really not a problem. What we're running into here locally lately is the climate is changing in that we don't get a lot of cool off. We get a lot of hot periods where we, even at night, we can't take advantage of night cooling anymore. That is, if you talk to climate people here locally, they can't substantiate that. And that just produces more load. You don't have a potential then at night to get rid of it. So I recommend to all of our clients right now, provide that active cooling element, and then you're set for those climate changes that may be happening and for the internal heat gains that you may have when you have a big party or you have a bunch of people staying over or something like that.
So in the house in the woods, you had put in like electric floor heat.
Mm-hmm.
Did you feel the need to do that in this house?
The question was there a need to do electric in-floor heat? And the answer is we already knew we were going to have hydronic, water-based in-floor heat. So then we wouldn't add electric in-floor heat here. So no, it's fine. That's just how the system works here. And it's thinkable to do a passive house retrofit without any in-floor heat. You don't have to have that. We actually have a new design that we're working on that's just going through pricing now. And that house is being heated with 2 mini-split heat pump systems for most of the time. On the very cool days of the year, there's baseboard electric resistance heaters. And the reason why we chose those is because they're very, very inexpensive. At the heat loads that we have in these buildings, $1,000 will buy you all the heating elements you need to heat that house on the coldest day of the year. So it's very, very cheap. The in-floor heating that you saw in that other house is, I would say that's definitely a step up. And that's for homeowners who want to buy that and who appreciate the comfort and they don't want to look at a baseboard radiator. But, from our experience, that's 4 times the cost. But that's fine. If that's what you want in your house, then that's good. Yeah. Question back there.
Quick one on spray polyurethane foam. You avoid that mainly just due to long-term environmental concerns?
Yeah, the question was to spray foam. Why don't we like it? It's true, there are environmental concerns because it's a crude oil-based product as it is. It has blowing agents and all of that. I think the off-gassing portion of that is, to me, it's still kind of a black hole. How good or bad is that, and when will it stop? A bigger issue for me really is also the air tightness and vapor retardation that's advertised with it, especially when you combine it with wood construction, simply because that stuff is rock hard. And we all know that wood expands and contracts as it goes through the seasons, and a wood structure actually moves a little bit. So what happens when those things come together over time, over 20, 30 years? Is that foam gonna crack or start to separate from that wood at one point? And I'm not sure that the verdict is fully in on that. I mean, BASF may prove me wrong on that, but I simply don't know. And so we try to err on the side of caution. But I will say that, we're thankful that we have access to it because it is a lifesaver, as you've seen in some of these assemblies. I've experienced it in my own house. There may be areas where you just can't get to them. Physically, there's not enough space to reach and try to do a good job with the cellulose or something like that. And then having a spray gun and being able to just spray that all shut is a lifesaver. So I think in the retrofit, that will play a role. That product will play a role. In new construction, we can eliminate that altogether. There's no need for it. And I should also mention there's a gazillion other products that we usually don't use here, but that are readily available. Mineral wool, wood fiber, recycled denim insulation products. And there's so much stuff out there if you just look. So it's very easy to substitute that out.
Yeah. And then one other one, did you have any issues using the OSB as basically your vapor retarder with the code officials or not?
No, I'm not sure if they understood that,
I
but that
think they
wasn't
glazed
questioned.
over when they saw the plan and just have at it.
They did not ask for the perm rating of the product, and they did not complain that it wasn't technically on the warmest side of the wall. It's on the warm side of the wall, but I mean, if you want to nitpick it, it is not on the warmest side of the wall. What I found though in Minneapolis, at least on the retrofit side, is that you can talk with these people, and if you can show them that you're making a better wall, and again, if we show them a hygrothermal model, I went through that on a basement in my own house, and you show them, we've really looked at this from an engineering standpoint, and this makes a really durable, good assembly. They're definitely willing to listen. But on this particular project, that question, I don't think
I
it was
think he
raised.
walked in and got the permit within 3 hours. I mean, it was just quick and easy.
Did you tape seams on both sides?
No, just on one side. Yeah, and that has everything to do with the quality of the tape that you use. If you're confident that it'll pressurize and depressurize to 100 Pascal either way, then that's fine. And I will plug Siga for their tapes because they make good stuff. I will say, however, that based on the OSB face that was facing out, some of the joints had to be primed, and the tape company makes it their own primer. And so when you say prime, it's not like an artisan craftsman. I mean, you slather the stuff on, you wait 5 minutes, and then you tape it. So I think it's a reasonable effort.
Yeah.
But it was an effort that initially we didn't think we had to go through, and it has everything to do with OSB formulations. And there are so many plants that make it, and they each formulate a little different, and so they respond slightly different to the taping. Yeah.
Did you give much thought, or do you, when you design a passive house, to other sources of energy and solar and PV panels and radiation and wind generators? Or is there so much insulation that you don't have to factor that in?
Right. So the question was, do we give any consideration to renewable or alternative energy sources, or do we just, make a really good building envelope and walk away? The short answer is that the paradigm we subscribe to is conservation first. We think that's the best resource and the cheapest resource. And so let's do everything that we can on that front first. And that's kind of an office mantra. And there's, schools of thought we subscribe to there. But after that, you're left with the remaining loads, and there's always some. There isn't a building that you just put in the landscape, and I shouldn't say any, depending on where you are on the globe, there might be, but not here. You can't build a house that completely self-sustains itself without external input. So that conversation is raised. The truth is, though, that when you have, in this case, access to natural gas, you have a very clean burning fuel. So you have a very low penalty for using that, and it can be burned in an almost environmentally friendly way. The one caveat is it's still a finite resource, but maybe not for the next 50 years. So continuing to use that in this scenario, I think that's something that we can stand for. We're not terrible people because we do that. But at the same time, I will say that we suggested solar thermal preheating was something that wasn't in the budget, but is something that could be done for a house like this. And we can also find that in buildings at that scale, you may be able to cover your own electric use footprint on your roof. The passive house in the woods, again, is a testament to that. You can, on your own site, generate enough, actually more energy than you consume on site. And you can only do that once you've gone to the level of a passive house or something like it. So we know that, and that is out there. It wasn't part of this project. It wasn't part of the budget, but it is part of many project discussions. Yeah. All right, I think I have one more question here from the web. Let's see, is it possible to do the project? Okay, I think the question is just to who all was on the team and whether we would publicize the people who were on the team. And to that point, I think if you go to the MinnePHit House website, I think they're all listed on there. So that would be, if you want to know who all worked on this project, go to that website. But basically, it was Ryan Stegora Construction, the homeowner. It was T Studio Design. Eric Bunkers was the structural engineer. And I think those were the only consultants and executing parties on the job. Yeah. All right. We've exhausted it. Good. I will turn off the webinar.